In the previous video, we obtained these two column vectors corresponding to data for various cars. And in this video, I want to investigate the question of to what extent is there a linear relationship between these two values, horsepower and acceleration. So let's first remind ourselves what these vectors look like. So for example, if I look at the 8th entry in each of these vectors, I get these two numbers here. And what's that telling me? Well, I looked up what acceleration stands for in this data file, and what it stands for is how many seconds does it take the car to get from 0 to 60 miles per hour. So a larger number for acceleration corresponds to worse acceleration. And just as a reality check, let's see where this came from in the original data file. So here's the 8th row of this data file. Here's the horsepower value. Here's the acceleration value. But notice those aren't the numbers that we got when we checked for what's the 8th value. We got 215 for horsepower and 8.5 for acceleration. So why are those different? Well, remember that we deleted all of the rows that contained a non-numeric entry. So the first row here, which is really a header row, that contains strings rather than numbers. So that got deleted. So the 8th row in the resulting vector really corresponded to the 9th row in the original spreadsheet. So here's that 215 and here's the 8.5. And what car does this correspond to? It corresponds to this car here, okay, a Plymouth Fury. And we're going to investigate, is there a linear function that takes as input horsepower and as output approximates acceleration in some accurate way? And we're going to do this using linear regression and least squares fit. And the mathematics behind least squares is really elegant, and maybe you've seen it before in multivariable calculus or in linear algebra. We're not going to look at the mathematics at all. We're just going to use it. So it's already built into MATLAB under the name fit linear model. And now I'm supposed to tell it what's the input variable. Okay, we're going to use horsepower as our input variable. And what do we want to be our output variable, our response? We want that to be acceleration. And let me name this result MDL for model. And we get this kind of complicated table of statistical data, but what we really care about is what's in this first column here. And this is telling me what's the y-intercept, okay, 20.7 approximately, and what's the x coefficient. Okay, we only have one dependent variable, so this x1, we could just call it x if we wanted. Oh, and I said dependent variable, I really should have said independent variable. So we only have one input variable, and the coefficient of that, like the m in y equals mx plus b, is estimated by approximately negative 0.05. And so I could just type those numbers out, but here's another way to get access to them. I can use what's called feval for evaluate the function. And let's evaluate this model. Let's just evaluate it at the input 0. And so I should get the y-intercept. I should get this 20.7 number. Yep, so that's working. And now let's plot these things. So let's plot the original data. So let's plot horsepower versus acceleration. Okay, and if I just look at this, it's going to be a mess. Okay, because it's connecting all of these different things that aren't laid out in any nice way, and there's no real reason to connect them. So let's not do it like that. Let's say not connected, and at each of the points of my data, let's have an O marker. And together with that, let's put the line that MATLAB is telling us using least squares best approximates this data. And then we can look at it and see to what extent does it look like this is a reasonable approximation. So again, input is going to be horsepower, but output, we don't want to use acceleration. We want to use this approximation given by the linear model. So we're going to do f-eval of the model of horsepower. Okay, so we're inputting to this f-eval model. Okay, so that's just some complicated way of saying here's a function whose input is x and whose output is 20.7 minus 0.05 times x. Okay, and we're applying that to each entry in the horsepower vector. And let's see how this looks. So these blue circles, these are the original data. And this red line, okay, it has negative slope because remember we said that the bigger the horsepower is, the better the acceleration is, so the smaller this number should be. Okay, because this number represents how much time does it take to accelerate to the speed 60 miles per hour. And yeah, so you can either use some of these fancy statistical data to estimate like how good is this model, is this too simplistic, or you can at least get some intuition by looking at this plot here that shows both the original data and the least squares linear approximation to the data. And I'll let you decide for yourselves how accurate you think this linear model is for this particular batch of data.